Hello, welcome back to the wonderful world of acid-base equilibria. This will be part 7. So in this one we're just going to kind of continue doing weak acid calculations and sort of learning a little bit more morphs of how you can do this and sort of what it means. And there's just a million kind of different angles that can be looked at, and so we don't want you guys to be surprised by what you see on the AP exam. So this is a really good example right here. What is the pH of a 0.15 molar solution of acetic acid? Well, pH is easy to understand that pH is the negative log of the hydrogen ion concentration. So all you need to do is figure out how much of this acetic acid is going to become hydrogen ions, and then just take the negative log of that concentration. So not real tough. But what we're going to need to do is we're going to need to set up an ice table in order to figure out value of X and substitute in Ka, which we can look up in Appendix D in your book. So in Appendix D, it's going to actually give you the Ka for this. So I did some of these calculations right here to save some time. So I set up the ice table, and you see, so the ice table, our initial amount that we put in is going to be 0.15 molar. And that's going in right here, and then that's going to translate out to 0 and 0 here initially. So of course this is going to subtract from X, and X is here's 1 to 1 to 1 ratio. So everything is ones in this balanced equation. So we're going to subtract from that 0.15 molar as this turns into these, and we're going to add these and these in equal amounts. So when we look up in Appendix D, we find that the Ka for acetic acid is 1.8 times 10 to the negative fifth. And we know that the Ka equals the product squared divided by the reactant, not including water. So here's what we do. We say, okay, well then Ka is going to equal X squared. There's X times X divided by 0.15 minus X. Now, you'll notice down here that I didn't put the minus X. I left it out. Now, why is that? The reason for that is because X is actually going to be really, really small, and it won't affect the answer because it's just so small. Now, how can you tell if it's small enough to not affect the answer to sort of do this shortcut? Well, the rule of thumb is really to say that if I is greater than 100, I being your initial concentration, so if your initial concentration I is greater than 100 times your Ka, then you're all right. So 1.8 times 10 to the negative fifth times 100 is still much smaller than 0.15. And if that's the case, if it's like well over 100 times smaller than this, it's not going to make enough difference to matter. And so just leave it out. So right here, so like I said, it should be 15 minus X if we're doing the ice table like officially and perfect, but we don't need to worry about that. So when we do this, we multiply this by 0.15 and then take the square root. We get 0.0016 molar. So that's the concentration of the hydronium ion concentration as well as the acetate ion concentration. So then what we can do is we can say, well, if that is the hydrogen ion concentration, the pH is the negative log of the hydrogen ion concentration. So insert that in there. And so you take the negative log of 0.0016 and you get 2.78 is your pH. So that was a pretty simple little process. Now to shortcut things, you don't need to really run an ice table, because honestly, anytime you do have to sort of kind of do that check and balance, like I said, of do make sure that your initial concentration is more than 100 times your Ka. If that's the case, then you're all right, and you can just use this. And this is that the Ka equals X squared divided by your initial concentration. So kind of a shortcut. This is the factors that your ice table would give you. So we're going to use that one more time in the next in the next idea right over here, the next problem. So here's the next problem. So hydrofluoric acid, also a weak acid. Combining with water is going to make hydronium and fluorine, going to be a weak acid. And here's our Ka. We can look this up in the back of the book as well. So here's the idea. What is the amount of moles of hydrofluoric acid that would be needed to form a 0.175 liter solution with a pH of 2.21? Well, here's what we have to do. We have to say, if we want this pH, then we have to have a certain concentration of hydrogen ions. And our concentration is going to be dependent on this volume. We're given a specific volume right here. So those are two things we need to worry about. We need to worry about the concentration of hydrogen ions and this volume right here. So first of all, what we can do is we can say, well, what is a pH of 2.21? Well, a pH of 2.21, we can actually get let's see if I did some calculation. I didn't do any here more. We can actually get the concentration of hydrogen ions by taking the pH and taking it to the antilog of the negative pH. So if I was to say, okay, what is the antilog of negative 2.21? If you type that into your calculator, you're going to get that's going to equal 0.0062. We'll round off there. So 0.0062. So that's the actual concentration of the hydrogen ions. But this is, of course, molarity. So we're talking about this is over 1 liter. And what we really want to know is how many moles am I going to need to do this in 0.175 liters, right? Because that's specifically how much we're forming. We're not forming a liter. And so then I would say, well, what is 0.0062 moles of hydrogen ion over 1 liter? But how many moles is that over 0.175 liters? So to figure out this answer, I'm going to cross multiply and divide. So I'm multiplying 0.0062 by 0.175, and I get 0.00108 moles of the hydrogen ion in 0.175 liters at that pH right there. All right, so what does that do? Well, that actually tells me the answer at that point, because if I know the moles of hydrogen ions, this is a 1-to-1 ratio. So for every mole of this that became hydrogen ions, it's a 1-to-1 ratio. So I lost 1 mole for every mole that became hydrogen ions. So that's it. So that's the answer. So it would take exactly this, 0.00, and let's round it off to keep significant digits. Actually, no, significant digits would take me out to 0.018. Yeah, so 0.018 moles is my final answer. And so that's the exact amount of moles of hydrofluoric acid it would take to create a 0.175 liter solution with a pH of 2.21. Yeah, so that sort of helps kind of do some weak acid stuff. I'm gonna do a couple more weak acid sort of explanations here, and in the next one I'm gonna do percent ionization. Should be a pretty quick one.